Thank you very much. We are very fortunate to have Professor Stephan with us. Mr. Stephan, good morning.
Good morning.
Yeah. So we are very fortunate to have you here with us. I'm Dr. Arup Kumar Das. I'm from IIT Roorkee. I'll be moderating this session. Okay, so let us wait for a couple of minutes.
Yes.
Then we'll be starting.
Yeah.
Thank you.
Shall I already try to share my slides?
Please try.
Let's see.
Yes, it's absolutely fine, visible to us.
It's fine?
Yeah, absolutely fine, visible to us.
Good. Let's see if I can.
Organizers, please let me know if I need to wait or I can continue at 1 p.m. because other sessions, parallel sessions are going on. I do not know the progress of those sessions.
Do you also see the laser pointer?
Yeah, I can see the pointer also.
Okay, that's perfect.
Sir, we can exactly start at 1 p.m.
Okay, thank you. So Professor Stephan will be starting with a small introduction from our side, and then I'll be sharing the, I'll be giving the stage to you for the presentation. Okay, so good afternoon to all of you. So we are now for the keynote lecture of Professor Stephan. So this is my pleasant duty to introduce Professor Stephan over here. In fact, as a researcher in the field of boiling heat transfer, we have admired the work of Professor Stephan. So we are fortunate here to get Professor Stephan, and he has spared time with us. So a short biodata I am supposed to read about Professor Stephan, though I don't think that is necessary for this forum for Professor Stephan. But still, let me go ahead like this. So Professor Stephan has studied mechanical engineering at the Technical University of Munich. He then moved to the Joint Research Center of European Commission in Ispra, Italy, as a Marie Curie Fellow, as PhD student. In 1992, he received his PhD in collaboration with University of Stuttgart. From 92 to 97, he worked in R&D for Mercedes-Benz. In 1997, he was appointed full professor at the Technical University of Darmstadt and director of the Institute for Technical Thermodynamics in the Department of Mechanical Engineering. Since then, Professor Stephan additionally worked in different part-time functions like Dean, Department of Mechanical Engineering, Director, Collaborative Research Center, called Interaction Between Transport and Wetting Processes, Senator of the TU Darmstadt, and spokesperson of the TU Darmstadt research field, Energy and Environment, to name a few. Peter Stephan has published many scholarly articles. Out of that, 3 are textbooks. Even I have also a copy of those books. More than 280 research papers. All of us are admiring his work. He has supervised more than 50 PhD students. He is member of editorial board of 4 international journals and was honored by several awards like prestigious Nukiyama Medal Award of Heat Transfer Society of Japan. He has received this award in 2012. The Golden Medal of Honor from the Association of German Engineers in 2018. And in 2020, he has received ASME Fellowship. The main research interest of Professor Stephan are heat transfer in multi-phase systems, heat pipes, heat performance heat exchangers, high performance heat exchangers, heat transfer in space, thermal analysis of coupled energy conversion systems. So we are going to listen Professor Stephan today. The title of the talk is Interaction Between Evaporative Heat Transfer Phenomena and Wetting Phenomena, Generic Experiments and Numerical Simulations Professor Stephan will be sharing with us. So with this small introduction, Professor Stephan, I request you to please start your talk. Thank you.
Thank you very much for this very kind introduction. Can you hear me? Is that okay?
Yes, absolutely fine, Professor
Perfect. So Yes, thank you very much for this kind introduction. You already mentioned the title. The title is written here, and what you see here below are two examples for wetting and de-wetting phenomena in combination with heat transfer. This here is drop impingement cooling, and this here is nucleate boiling. Both videos show numerical simulations, results of numerical simulations. And with the next slide, I would like to show what they have in common. They have in common that here during the spreading and receding meniscus contact line, as well as here, you have this moving three-phase contact line on a superheated wall. Superheated means superheated against the saturation temperature in the gas phase, in the vapor phase. So you have evaporation here, and at the same time, you have a moving liquid vapor interface at a hot wall. And the question now is, what about the conjugate heat transfer between the hot wall, transient, of course, transient conjugate heat transfer, and the two-phase liquid, and the phase change, so the evaporation. What is the evaporation rate, and how does the evaporation rate depend on the movement of this contact line here in the different situations, the situation of wetting and the situation of de-wetting? Now, the contents of my talk. First, I will give a short summary about the state of the art. I will briefly introduce and remember all of you about the knowledge for interactions of heat transfer and wetting and de-wetting situations, the major influencing aspects here, and the major research questions. Then I will go into a second part of the presentation where I will present two generic experimental setups. They both have in common the heater device, as you will see later, but they are quite different by means of the application behind it. So first experiment is a nucleate boiling experiment, and the second experiment is a drop impingement experiment onto, of course, a superheated wall, including evaporation. And I will explain also the numerical modeling approach that was developed in parallel to learn from both of it, from the generic experiments with high spatial and temporal resolution, as well as from the numerical simulations. And I will present results in an exemplary manner on different length scales, a little bit for nucleate boiling, but basically due to time reasons for the drop impingement experiment and numerical simulation. Now, first part of the presentation, what do we understand today? What is state of the art? State of the art, and we quite well understand dynamic and wetting processes and de-wetting processes, but basically only for pure fluids on smooth surfaces and under isothermal conditions. So as an example, I show here a plot of a contact angle hysteresis, so a contact angle, three-phase contact angle at a wall, isothermal wall in this case, on a smooth surface with a pure fluid, depending on the contact line velocity or the capillary number by means of non-dimensional numbers. So here we have a wetting situation, and here we have a de-wetting situation. In a wetting situation, typically with increasing wetting velocity, the contact angle is increasing, and here with increasing de-wetting velocity, the contact angle is reduced. And then we can have a hysteresis, depending also on surface roughness effects and so on. But basically, this is valid only or developed only for smooth surfaces. So we never in experiments, of course, or in the real world, we have perfectly smooth surfaces. That's why we can have also contact angle hysteresis. This is quite well understood. However, we do not fully understand those dynamic wetting and de-wetting characteristics under non-isothermal conditions and with high heat fluxes and high evaporation rates. And as an example, I show you the results of which were published in 2012 together with one of your colleagues from India, Bishirai, Kunkelman, Stephan, Plowski from the United States, and Jungwoo Kim, and myself, of course. And here what we plot is the measured apparent contact angle depending on the wall superheat. So this here, zero superheat means isothermal system, complete system is isothermal. And we put an FC72 perfluorohexane droplet on a surface, on a copper wall. And we measure with delta T 0, so no superheat, we measure approximately 10 degrees contact angle. However, if we increase the wall superheat, the contact angle that we measure is increasing. So top contact angle, even though this is quasi-static, here in this situation, we measure then here 30 degrees. So a quite big difference when jumping from isothermal conditions to 10 Kelvin superheat, from 10 to 30 degrees contact angle. And what we also see in this plot, at the isothermal conditions, it's basically independent from the oxidation grade of the surface. However, at higher temperatures, also the oxidation grade, either non-oxidated or slightly oxidated, medium oxidated, also changes, has an influence on the contact angle. So under non-isothermal conditions, the situation is quite different than under isothermal conditions, where the majority of the correlations, for example, for contact angles are developed. What we also do not fully understand, apart from that, what I said before, is the dynamic wetting and de-wetting characteristics for complex fluids and for complex surface structures or structured surfaces. This, however, is not the contents of my talk today, but you mentioned in your introduction that I'm also the head of a collaborative research center here in Darmstadt, financed by the German Science Foundation, which is called Interaction Between Transport and Wetting Phenomena. And there we typically investigate numerically and experimentally complex fluids and also complex surfaces. And such a collaborative research center means that approximately almost 20 PhD students are working in this field, together from different disciplines, from material science, from chemistry, from mechanical engineering, from mathematics, etc. Now, what are the major influencing effects on the two-phase or evaporative heat transfer? In the past, about 6 years, an ESA from the European Space Agency, an international topical team, ITT means International Topical Team, that is a bunch of European colleagues, but not only European colleagues, also colleagues from all over the world. And the European part, we get small financial funding for this international topical team. And we all together developed a roadmap for the two-phase heat transfer, evaporative heat transfer, for the European Space Agency to, well, the aim of the roadmap was to show them the scientific questions that they might address also in zero-G experiments in space, which I will show in a minute. And we together categorized the major influencing aspects into three categories. First, the fluid alone, then the wall alone, and then the interaction between fluid and wall. And there are different issues, for example, considering only the fluid, the two-phase fluid, of course, liquid and gas. We have transient, to address with our questions, transient convection, liquid vapor interface dynamics like bubble or droplet dynamics, like mergers, for example, coalescence. We have to address liquid vapor interfacial instability. And in case of multi-component fluids, we have to address, for example, Marangoni effects, also the multi-component gas atmosphere additives, and so on. On the pure wall side, we have to address transient conduction effects inside the wall geometry, of course, and the surface chemistry or topography, roughness effects, small scale structures, etc. of the wall. And in between, for the interaction between wall and fluid, we have to address, for example, heterogeneous nucleation of bubbles or droplets. In case of condensation, it was also addressing condensation. Of course, we have to address the wettability characteristics of the fluid on the wall. We have to address the microscale conjugate heat transfer, which is basically influenced by microlayer formation or by contact line heat transfer. and we have to address adsorption, for example, adsorption effects. And for all these different subcategories, A1 to A5, up to C1 and C3, we then developed scientific questions. This is a bunch of questions, which of course I won't go through that here in this talk. We defined 31 questions in these different categories, and I give only 3 examples here. So in the category fluid, we, for example, posed this scientific questions A32. A3 is on liquid vapor interface dynamics. And we said we want to answer with our research, with our joint research, we want to answer the question, what are the effects of coalescence or breakup on local heat and mass transfer on the fluid side? On the fluid-wall interaction, for the category microscale conjugate heat transfer, contact line or microlayer heat transfer, we posed the questions, how does local heat transfer influence the wetting characteristics, and especially also vice versa? So heat transfer has an influence on wetting characteristics, but wetting characteristics also has vice versa, an influence on the heat transfer. And in the category C, for example, for C1, transient heat conduction, we posed the questions, what is the influence of the thermal characteristics of the wall material? For example, thermal diffusivity of the wall. So we collected a number of questions, and with our joint research, we want to answer these questions. Now, this brings me to the second part of my talk, the generic experimental setups that I will introduce and the numerical modeling approach. First, this here shows both the result of the simulation and the result of the drop impingement experiment. So we developed generic experiments here for drop impingement. I will explain in a minute how this experiment looks like. And then we observed the drop impingement process with a high-speed black and white camera, and we observed the temperature profile as well as the heat flux profile with an infrared thermography. And on the same with the same generic setup, we developed a simulation, and then we compared simulation with the experiment. We did exactly more or less the same for the nuclear boiling situation. So in the nuclear, here you see some simulation results, and here you see some experimental results. For the nuclear boiling experimental part, we developed 2 experimental setups. One experimental setup that we use in our lab here on ground in Darmstadt. And we use this experimental setup also in parabolic flights where we can vary the gravitational forces. Additionally, together with an international team, we developed an experiment, a boiling experiment for the International Space Station. So this experiment has flown on the International Space Station last year. I can present some results of this International Space Station experiment. Meanwhile, the experiment came back to Earth. It's in our lab now again, and we hope to bring it up next year again into space with other kind of fluids, with other kind of raw materials, etc. Now, first then, let me present the basic idea of these 2 experiments. I will start with the nuclear boiling experiment, and I said we have one setup in the lab, which we use in the lab and for parabolic flights, and we have one setup developed in an international team for the International Space Station. The basic idea in these 2 versions of the experiment are the same. So we have a transparent infrared heater, which I will show, I think, 2 slides later from now on. And on this transparent heater, we can apply heat. We can have a short pulse of a laser to nucleate a bubble here. And the bubble, once it's nucleated, it is growing, the bubble. And then either we don't have a flow, then we have pool boiling, or we have a flow here, then we have a flow boiling situation. We have a high-speed camera to observe here the shape of the bubble. And we have a microthermocouple rack with different tips here, very small microthermocouples of less than 50 micrometer diameter to measure the temperature in the different positions in the 2-phase fluid. So also if the bubble is growing inside the bubble or outside the bubble in the thermal boundary layer. What you see here is, of course, for the International Space Station, the experiment has to be very small. So the experiment fits here into this tiny box, while in the lab, the experiment uses several square meters of space or cubic meters of space. Here it's simply in a small box. And this box was brought up into space in late 2019 with a rocket from the United States. It was brought to the International Space Station here, and here the Italian astronaut is mounting our experiment. And here you see now the control center that we had here on Earth to control the experiment, to get the data, and also to change parameters on the International Space Station. So we could actively control the experiment on the International Space Station and then observe the results. The basic idea of this heater concept, and with the two cameras, infrared camera and high-speed camera, is the same in our drop impingement cooling experiment. So in the drop impingement cooling experiment, we developed a test cell that you can see here. Inside this test cell, we can control the vapor atmosphere with the pressure. So it's a pure vapor atmosphere here in this test cell. And we have a small droplet generator, which can create single droplets. And then we can, these droplets fall onto the heated infrared transparent heated plate. And we can have either single droplets hitting here or multiple droplets, one after each other, or also meanwhile in parallel. Today, I will only present single drop impingement here on this heated plate. Again, we have such a high-speed infrared camera with a backlight illumination, so we can observe with a very high temporal and spatial resolution, 1000 Hertz, and spatial resolution 14 micrometer per pixel. We can observe here the dynamics of the drop impingement event. We have this in infrared transparent heater, and then also with the same time resolution, an infrared, high-speed infrared camera, and we can observe then the temperature profile. On the next slide, we will see this specific heater, which is basically almost identically for both experiments. Here you can see the heater that we developed for this International Space Station experiment, but as I said, the heater is basically the same in all the experiments. So the heater itself consists of the base of the heater consists of a calcium fluoride substrate, which is basically fully infrared transparent. So we can view with the infrared camera, with the high-speed infrared camera, through this glass plate. In case of the nucleate boiling experiment, we produce with a laser beam a small artificial cavity inside this calcium fluoride glass, so of 20 micrometer diameter and about 100 micrometer depth. Of course, in case of the drop impingement experiment, we don't have this nucleation site here. Then the interesting thing is that this calcium fluoride glass has very similar thermal diffusivity as, for example, stainless steel. So the thermal behavior of this infrared transparent glass is very similar to that of stainless steel. Then we cover this infrared transparent glass with a chromium nitrate layer of only a little bit less than half a micrometer, 400 nanometer. And this has basically an emissivity of 1. So when we observe here with the infrared camera, of course, fully calibrated, pixel-wise, in situ calibrated, we observe here a temperature profile. Then we measure basically the temperature profile at this chromium nitrate emissivity layer. On top of this chromium emissivity layer, we coat a pure chromium layer for the heating purposes. It's also about 400 nanometer thick. And then we contact these chromium layer with the electrodes. So what you see here, basically, these are the electrodes. We have 4 electrodes, 2 on each side of the heater, which are contacted here on the pure chromium layer. And then we have here the heating system on top of this infrared transparent glass. And by applying voltage, we then have, through these electrodes, we have a Joule heating. So we have a heating here and a temperature profile measurement possibility directly at the heater surface. Now, from this infrared camera, we get, of course, with the calibration, as I said, in situ calibration and pixel-wise calibration. That's very important for accurate measurement. We get in each time step, tau, and on the surface in X and Y direction, a 2D profile of the temperature. Now, the boundaries of this infrared transparent glass, as they are very nicely isolated or in a very, very low pressure atmosphere underneath, this means they are basically considered to be adiabatic. And with this assumption, we can then, from the transient temperature profile, 2D temperature profile, we can numerically compute the temperature profile 3D here in the entire heater system, including the Joule heating in the chromium layer on top. So from this infrared temperature data, we get also, as a result, the transient 2D heat flux profile at the interface of the solid heater. So we have both temperature and heat flux profile. Now, let me talk, before I present results, about the basic model for numerical simulation. And again, here, the basic model, of course, is a little bit different in case of the nuclear boiling situation compared to the impingement cooling, but the basic codes are almost identically. So we subdivide our region of interest, either the nuclear boiling test cell or the drop impingement test cell, into a more macroscopic part and into the contact line part. For the contact line part, we use a subgrid dynamic contact line model. Because this is on such a small scale, we can't include it due to computational time reasons into the overall model. So on this subgrid dynamic contact line model, we model this small area here, including the evaporation. We consider mass, momentum, and energy balances, including the adhesion forces by means of a disjoining pressure here, which reduces the volatility of the fluid. And then we have a flow from the bulk here towards the contact line and evaporation here. And of course, the wall can move. So, there's a relative motion between the interface, the liquid vapor interface, and the wall. So we can have either advancing contact line or receding contact line. So, and this solution then is parameterized and then matched into the larger scale model, which is a CFD computational or CFD simulation. We use an open foam, specifically the interfoam version of open foam. And we included our own phase change model, our 3D interface reconstruction we further developed, and we use adaptive grid refinement, of course, because we have to have a very fine grid close to the contact line and a much coarser grid outside this region. So this is the basis of the model. Now let me come to the results, exemplary results on different length scales. First of all, on the pure contact line scale, so only from the dynamic contact line model. What I plot here is the contact line velocity. So 0 means static contact line, positive values means advancing or wetting, and negative contact line velocity means de-wetting or receding contact line. And we see here this apparent contact angle in this microscale, from this microscale model, and different wall superheat. So 1 Kelvin, very small superheat, up to 20 Kelvin, while the big superheat. And what we see here, the contact line, of course, increases in the advancing situation, so in the wetting situation. And if you de-wet the surface, then of course, it's going towards 0, it's very small. And if you increase the superheat, that's what we saw also in the very beginning of my talk, from this publication about 10 years ago, then we see that with increasing superheat, the contact angle is increasing. And of course, this we can use as a parameter study and then include it in the larger scale model. And what we also put then as a parameter table into the larger scale model is the heat that is transferred by per contact line length. And you see here that in the advancing situation for positive contact line velocities, so wetting situations, there is less heat per contact line length transported than in the receding situation. And this is quite obvious because in the receding situation, you also have a smaller contact angle. So you have a thinner film, and thinner film means higher heat transfer. Now, this here shows results from the nucleate boiling simulation, including, we only see here the simulation from a macroscopic point of view, but this includes also the contact line model, which is used as a subscale model in the larger model. And we can distinguish three periodic phases. The first phase is the advancing, or the receding contact line, excuse me, so the de-wetting situation. After nucleation, the bubble is growing and it de-wets the wall, so we have a receding contact line situation. Next, we have a re-wetting phase, so an advancing contact angle just before the bubble is detaching. It's you have a re-wetting situation at the wall, so an advancing contact line. And then we have subsequently a detachment phase and a waiting time for the subsequent nucleation. Subsequent nucleation starts when the local wall superheat at the nucleation site is high enough to generate the next bubble. And then we have these, again, we're repeating in periodic manner, these three phases: de-wetting, re-wetting, we are receding and advancing contact line, and then no contact line at the wall, just waiting time for the next nucleation. On the next slide, we see a very similar video, but now for the drop impingement case. And also here we can distinguish three subsequent periodic phases. When the drop here is approaching the superheated wall. Sorry, this here is German. So Wandüberhitzung in Kelvin means wall superheat in Kelvin. So the wall is superheated here about 11 to 12 or 13 Kelvin compared to situation, and the drop is approaching the wall. Now, then the drop is hitting the wall, and first we have an advancing contact line, or the drop is wetting. So we have a wetting phase. This phase is inertia driven because you have inertia from the velocity of the drop that is hitting the wall. The next phase now is the de-wetting phase. This is surface tension dominated, surface tension driven, because after the drop has spread to maximum radius, it's shrinking again. The base radius is shrinking again because surface tension tries to put the droplet into an equilibrium position. And then after reaching this equilibrium position, due to the first inertia and then surface tension driven, you might have small oscillations, but then you have basically a sessile droplet that is slowly evaporating further. We see this also here in the next slide quite nicely. We see now the drop will come down, and then we see two plots, which I will explain in a minute. The blue line is the mean temperature profile in this area, and the green line is the mean heat flux profile. So here, when the drop hits the wall at this position here, at this time, we see that the mean wall temperature, mean means it's all over this field of view, it's averaged on this field of view. We see that the drop is cooling the wall, so the temperature is decreasing, and the heat flux is increasing due to this cooling effect of the impinging drop. So we can observe this quite nicely. And this window here shows only a part of this window. So here you see, what you also see quite nicely is a kind of ring-shaped area with low temperature or high heat flux, which is close to the contact line. So at the contact line, we have the highest cooling rate, the minimum temperature, or the maximum heat flux near the contact line. Once again, to finish the slide, here you see the cooling effect and the increasing local heat flux. Now, if we compare these experimental values with our numerical simulations, it fits quite nicely, and we can distinguish again these three phases very nicely. The first phase was the initial spreading phase due to these inertia phases. So this is the radial position of the contact line versus time in milliseconds. And we see here, okay, the droplet reaches a maximum base radius, the radial position here, a base radius of about 1.6 millimeters in this case here. And then we have the receding contact line phase due to the inertia phases, and then here the sessile droplet that is slowly evaporating. And we see here the error bars, the uncertainties from the experiments. Of course, we repeated the experiment several times, and within these error bars, we see some small experimental variations, and this is the result, the red line of our numerical simulation. So it fits very nicely, and we can distinguish these three phases. Now we can use our numerical model to study very nicely different parameter effects. In this example here, I plot basically the same than in the plot before, but only numerical results, and I varied the pressure. Varying the pressure, and here the relation of the system pressure to the critical pressure of the fluid is plotted, shows quite interesting results. So the first phase, which is the spreading phase up to the maximum contact line values, is basically not influenced by changing the pressure. However, the second phase, which is the surface tension driven phase, the receding phase, it's quite influenced by the pressure. Why? Because the pressure has an influence of with the higher increasing pressure, you have lower surface tension, and you have typically larger contact angles. Due to these larger contact angles and lower surface tension, this spreading phase here, or the receding phase, is increased in time, so it lasts longer, and the minimum radius here then is also quite smaller than at lower pressures. So the pressure has no influence basically on the inertia-driven phase, but it has an influence on the surface tension-driven phase. Oops, okay. Now we compared in this drop impingement experiment the heat transfer. Of course, in the experiment, we can measure only the overall heat transfer on the entire wall. That's what we did here. And we compared that, then this is the stars. And the blue line here is the experimental values, and they also fit quite nicely. But of course, then we can see also in the different phases, where is the heat going to? In the experiment, we can't distinguish what is evaporation, what is pure convection, single phase convection. But of course, in the numerical simulation, we can distinguish between these different paths of heat transfer. So after the validation that the overall heat transfer of the experiment fits very nicely to the simulation, the experiment fits to the validation, we can trust the numerical simulation, and then from the numerical simulation, see what happens in detail. In the advancing phase, in the advancing contact line phase, in the inertia-driven contact line phase, the drop is hitting the hot wall, and we have a flow inside the drop, which is looking like this. So from the bulb towards the contact line, and this flow is pressing down the thermal boundary layer because we have a hot wall. So in this phase here, A, the thermal boundary layer is heated up quite a lot from the hot wall, and the liquid pushes down this thermal boundary layer towards the wall. Now, when we change the velocity to the surface tension driven phase, or the de-wetting phase, or the receding contact angle, then this hot fluid from the thermal boundary layer, because we have a flow in the opposite direction, basically, this hot liquid here is transported towards the interface, towards the liquid vapor interface. So the liquid vapor interface here is typically the temperature of the original impinged droplet, while here it gets a lot of heat, and temperature is increasing at the interface due to this flow from the thermal boundary layer. And that means if we look into a Sankey diagram, how the heat is transported, we see that in the first phase, in the wetting phase, the heat that is coming from the wall is basically going into latent heat, as latent heat into the fluid. So it's heating up the fluid here, the thermal boundary layer, basically. While in this phase, in the second phase, the fluid is already quite hot, the liquid is already quite hot, but now the hot liquid is transported towards the interface, and that's why we increase evaporation. So here, heat transport mechanism is basically purely convective heat transfer from the hot wall into the pure liquid phase, while here in this de-wetting phase, we start to have a high evaporation rate. And we also see what is directly transported, that's the wet arrow bar here, what we see what is directly transported through our subgrid model of the contact line, which is also increasing here in the de-wetting phase because due to this velocities and the thinner film, of course, we have higher heat transport here in the contact line model. So quite some different situations in these two cases. Now let me give a short summary of my talk here. First of all, we saw that we developed different generic experimental setups to study evaporative heat transfer for a single drop impingement, also multiple drop impingement, but I didn't show that here in this talk, and nucleate boiling. And both have wetting and de-wetting processes. And this is a more general thing in these different experiments. Then we developed in parallel numerical models, including a subgrid model for the dynamic contact line heat transfer. And the combination, I think the combination of the experiments and simulations specifically gives quite deep insight into the local flow and heat transfer paths. I showed you the different paths in the wetting phase and de-wetting phase. So in the wetting phase, basically it's convective heat transfer. And then in the de-wetting phase, the evaporation rate is increasing quite a lot. So these is basically, among others, the two results that can be withdrawn from these studies. During the wetting phase, advancing contact line convective heat transfer mechanism is dominant. Heat from the hot wall is transported into the liquid boundary layer and accumulating there, thereby increasing the sensible heat in the liquid. Evaporation rate is rather low in the wetting phase. During the de-wetting phase, however, so with the receding contact line, the evaporative heat transfer mechanism is dominant. The hot liquid boundary layer is spread towards the liquid vapor interface. As a result, the evaporation rate is increasing, thereby rejecting the accumulated heat from the liquid into the vapor core, into the vapor phase. Now, finally, let me thank for financial support, specifically for the European Space Agency and the German Aerospace Center that sponsor our space experiments, and then for two collaborative research centers that we have here in Darmstadt. One is interaction between transport and wetting processes. The other is droplet dynamics under extreme ambient conditions. And specifically, I have to mention that, of course, the work I presented here was not done by myself alone, but with a lot of co-workers around me, like Axel Silav, Tatjana Gammayer-Neusmann, Stephan Batsdorf in the past, Ali Reza Goliani in the past, Christiane Slavicek in the past, now Hendrik Sontheimer, and also Ganesh Gugila, thanks to these persons in my lab. And with that, I finish my talk and I'm ready to answer questions. Thank you very much.
Thank you, Professor Stephan. This was really very nice talk. You have first stimulated us with the open questions, and then you have linked up nucleate boiling as well as droplet impingement cooling through experiments and numerics. So I can see that some questions are there in Q&A, so I'll recite it for you. So Mr. Debartha from IIT Kanpur, he's asking, in the nucleate boiling experimental setup, what was the role of the electrode shown in the schematic?
Okay, I understand. I go briefly back as fast as I can. So we have to bring heat into this glass. This is kind of transparent heater, and we need to heat here the surface to get a certain superheat. So we have these electrodes here to contact this heating layer, this chromium layer. And by applying then voltage, and electric current flowing here through this chromium layer, we generate heat here in this layer.
Yeah. So he's also asking that was the microgravity drilled for nucleation site done after the two coating or before?
It was done before the coating. Directly into the glass, because we tried both. If we do it after the coating, then we destroy the coating due to this laser beam milled situation. So we really do it, I think it should be here, yeah. We do it before the coating, yeah. But when we coat it, the nucleation site, this artificial nucleation site, is getting a little bit smaller due to this coating, but it's still there.
Yeah. Delegates, you may please type questions for Professor Stephan in the Q&A section. So I got another question, Professor Stephan. Mr. Prashad Kangude is asking, how do you see contact line dynamics changes from hydrophilic to hydrophobic surfaces?
Well, we basically, in this study, first of all, I have to say, we basically have very hydrophilic situations because we typically use this fluid FC72, which is more or less perfectly wetting. Yeah. We meanwhile work also with other fluids in this collaborative research center and also with hydrophobic surfaces. In the hydrophobic surfaces, the situation is a little bit different because typically what we investigate here is apparent contact angles up to 40 degrees. So hydrophobic would mean that we are 90 degrees or even above, yeah. And then we don't have these strong influence of the moving contact line anymore, at least concerning the heat transfer. Yeah.
Yes. So one more, let us take Mr. Praveen Sharma is asking, researchers claim increase in critical heat flux in pool boiling using highly weighting fluid or nanofluid, etc. It is expected that the fluid weights the heated surface during heat transfer with increased heat transfer. So what is your comment on that?
Yes, my impression is these highly weighting fluids and specifically nanofluids. First of all, nanofluids somehow you have absorption of nanoparticles on the surface. And this absorption of nanoparticles on the surface means that you have more nucleation sites, which increases then typically the critical heat flux, and you have a better wetting. So, this can, of course, can be seen in the experiments too, that we have an experimental setup that I didn't show here, but also in other labs, these exist, where we have some microstructures on the surface, and if you increase the velocity of the wetting situation, yeah, then you increase the critical heat flux typically, and there are different methods to do this.
Yeah, so I understand the time is up, but still one more question, as because we get very less opportunity to interact with you. So Mr. Sanjeev is asking, physically, how accurate is the initial condition utilized for nucleate boiling simulation? Presently, is there any requirement for better initial condition for the same?
I'm not 100% sure if I got the question correct. So the initial conditions for the boiling experiment, basically. Yeah. Well, the initial conditions are such that how can I show that? Maybe here. Yeah, I can show that here. That we heat up the fluid first. Yeah, we have this preheater here, and then by preheating the fluid, we heat the fluid up to almost saturation temperature. Almost saturation temperature. And then we set, let's say, a subcooling of 1 Kelvin or 5 Kelvin and measure, of course, the subcooling with a microthermal couple rack. Yeah. Then we heat up the infrared transparent heater when we measure the temperature up to saturation or slightly superheat, 2 Kelvin, 5 Kelvin superheat. And then if we don't see a bubble, and typically we don't see the first bubble, then we inject a small laser pulse, yeah, some very, very small pulse, and then we initiate the bubble. Yeah. And then after that, it's bubbling from itself. We don't need the laser anymore. Then it started once, and then it's fine.
Yeah. So I can see that one more is there. If you allow me the last question I'll be asking, I understand I'm bothering you. So Mr.
No.
is asking that why the contact angle of the droplet increases on increase of superheat?
Why the contact angle increases? Yes, the contact angle is increasing. Basically, if you increase superheat, you increase the evaporation rate. Okay, and if you increase the evaporation rate, you suck more liquid from the bulk into the contact line area. Yeah. So the flow from the bulk towards the contact line area depends on the wall superheat. And the higher the wall superheat, the higher this flow from the bulk into the contact line area, and thereby you increase contact angle. That's a hydrodynamic effect related to the evaporation rate.
Yeah. So I see that there is no other question. Just a quick question, if you allow me from my side,
Yes.
that for subgrid scale model, whatever information you are giving to your interform code, so what are the informations we are passing from subgrid scale model to interform code?
We are passing informations in both directions. So okay. from the large scale, from the open foam code, we pass the wall superheat, the local wall superheat. And from the local wall superheat in the contact line area model, we do all these calculations, these numerical calculations with the Ruben-Kutta method, and then we pass the apparent contact angle, yeah, and the heat that is transported into this small area, sub-micrometer area. And these two values are going back to the open foam code. Okay. And thereby local wall superheat, heat transfer, and contact angle are related.
Okay. So thank you, Professor Stephan, once again for your nice talk and time for this conference. So I'm sure that conference organizers will be thanking you separately, but on behalf of session chair and other participants, delegates, we thank you once again for your stimulating talk. Thank you very much.
Thank you very much. Thank you very much.
Thank you.
Well, I have to close my window, I think.
Yeah, that is already closed. It is not shared with us.
Okay, good.
So with this, we conclude this session. So session 3 concludes over here. Thank you, all the participants and delegates. Have a nice time in the conference. Thank you, Professor Stephan. Bye.
Thank you.
Yeah, thank you so much, sir. So we have ended the session 3 now. So we will be meeting in the next